So in this session, we're going to cover a few things. First of all, we'll talk about the importance of stream processing in general. And then we'll talk about why Apache Flink is becoming the standard and the most adopted platform for stream processing. And finally, we'll see a quick demo of the product. So let's kick it off and start with why stream processing is important, or what you can do with it. So there are four key capabilities of a complete data streaming platform, as you can see here. First of all, there is the stream, which is basically the streams of data that is flowing into the system, into the platform. The second capability is connect, is the ability to connect streams and data from various applications and sources. And then there's the governance, the ability to govern the platform. And the one that we're going to focus today is the process part, is the ability to manipulate and do things with the data streams. And this is what we're going to focus on today with my presentation, at least. So to understand how stream processing fits into the data stream stack, we can compare it to the data at rest stack, okay? With the data in rest stack, we have, as you can see in the slide, we have, first of all, in the storage layer, the file system. But we are, as developers, when we are writing our application, we don't interact usually directly with the file system. That's why we have the databases, which we all know, love, hate, whatever. But we do the SQL queries, and then we can do the aggregation, filtering, and so on. And this is how we're interacting with our data that sits in the files. If we take it to the data in motion or the streaming applications, in the storage layer, we have Apache Kafka, which the data sits in the topics, as we all know. And the streaming applications can interact with the data, with the storage layer, with the streaming process, with stream processing. And the stream processing is the compute layer. And there, actually, Flink is one of the stream processor that can do filtering, joins, and aggregations, exactly like we do in the Kafka data at rest analogy, okay? So what are actually the benefits of stream processing on top of Kafka? So when we come to organizations, and probably you can see it in your organization as well, usually we process data down the stream, and the data goes from the application, the operational applications, to and pipes the data into some data store. And then the processing is actually done on top of the data store, okay? So this can work for a lot of use cases and applications. But there are some problems with this approach, okay? First, you might be adding latency for your applications because you're doing batch processing, right? You're not doing real-time processing. So you might be processing stale data, which doesn't make sense for all applications, okay? But the problem even becomes intensifies whether you start to fan out your data to several applications or systems. Then you need to do additional processing of the same data, okay? And this causes complexity, redundancy, and can cause also inconsistency. And of course, this all reflects also in cost, okay? It adds cost to your solution. And this is why it's so important to use stream processing, because if we look at this architecture, we want to try and process the data as fast as we can, as the data is actually generated, okay? And then we have few benefits, okay? First of all, for your first application, as you write it, you're actually processing data in real time, okay? Because then you're actually doing the processing immediately and not doing it in batch. And again, like mentioned before, you get also the benefits of not doing redundant and again processing the same data again and again. You're doing it upstream. In other words, you're doing the processing once and you're doing it correctly, then you enjoy the benefits of doing it just in the as the data is generated. This is another way to visualize stream processing and how it can interact with the application. I know it looks a little bit complicated, but it's really the same thing, but a different visualizations. Excuse me. As you can see, data is coming from the left, and it can be processed, filtered, and so on, and used by the, I hope it's pink or something like that, purple, I don't know, applications, and it could be used by various applications, okay? So you actually transform, enrich it once, and you can use it by various applications. And further, you can even, like take this join data, enrich data, and even process it more and use it by other applications. So this is very efficient way of doing your processing instead of doing it further down the pipeline. Okay, so what actually you can do with Flink? Okay, so there are a lot of use cases that you can address with Flink or with stream processing. As you can see, there's three main categories that you can look at. There's event-driven application, real-time analytics, and streaming data pipelines. For event-driven application, actually applications react to individual events or event patterns, okay? Which trigger computation or state updates and external actions. What do I actually mean? It's like, let's take, for example, fraud detection. Like if I swipe my credit card, more than 10 times in 30 seconds, that doesn't make any sense, okay? So we want to find these kinds of events and then act to it, okay? Maybe send an alert, like close my account, close my credit card, or pause it, or whatever. So this is event-driven application. For real-time analytics or streaming analytics, it's another key use case for Flink. It enables analyzing data stream as they arrive to the system and to derive a more actionable business insight. Example use cases that you can find there is monitoring campaign performance or tracking sales trends and things like that. You can actually create real-time dashboards on top of your data because you can do materialized views on top of incoming streams. And the third and last category is streaming data pipelines. It is actually a continuous ingestion and transformation of the data to create a more enriched and high value streams that you can further process. Example use cases are machine learning pipelines and continuous ETLs, okay? So actually it's what we actually saw in the bigger visualization. It's actually, it looks like continuous ETLs or ETL pipelines. Okay, so how can Flink help us do and help us in these categories? So Flink or frameworks like Flink support powerful SQL, but not only. I'll talk about it a bit later. They can give you powerful SQL operators that allow you, the developers, to perform complex analytics and manipulations on this on streaming data, actually in real time. So you have like built-in functions and operator that can address these categories that I just talked about. And if we look here, we have, for example, the match recognize, which help us to identify this stock pattern. Okay, I don't know if anybody hears about stocks. So this is looking for a double bottom pattern. And if we find this double bottom pattern, we want to have like an event and maybe buy the stock or sell the stock and so on. We can also do hopping windows, tumbling windows, and other capability that we have in Flink and SQL, and to address or do actions in cases that, like we have a pattern or things that we, like I said before, like do a select count of the credit cards swipes. So we can do that as well, do it with aggregations and so on. So for the second category, for streaming analytics or real-time analytics, we can actually create materialized views, as we can see here. We can see that we have like data that is flowing in, but we want only to understand which account has, like the most transactions, or see a dashboard. So this can be created easily by data that is flowing into the system. We just create a simple select, and we get a dashboard that is continuously updated, and we can see the benefits in real time. We can track everything in real time. So this is the second category. And finally, for streaming data pipelines, we can do joins, aggregations, and transformations to create new enriched streams. Okay, so we're actually taking the streams that are coming into the system and creating new higher value streams. We can also create fan-out queries, meaning that we can take data that is coming inside the system and create duplicates of the same data, or taking the data and transforming it, taking the same data and maybe taking several fields and want to give them access to other applications. So this is something that we can do. And we can also query from multiple Kafka clusters. So we can actually aggregate from multiple Kafka cluster into a single table that we can then query. Okay, so now that we have maybe the motivation of what we can do with stream processing, let's talk about why Flink is actually coming the standard for addressing this use case, or for stream processing. So first of all, if we look at the graph of the adoption of Flink, we see a similar adoption curve that we see for Apache Kafka, okay? So this gives us a good sign that this is something that is adopted by the industry, and this was a good evidence also for Confluent to adopting Flink as its major stream processing platform. We can also see that this has been adopted by the most innovative companies that we know, including Wix, that we'll talk about it a little bit later, but also Uber, Netflix, and so on. And these companies are using the mix of Kafka and Flink together to get the best value and do the real-time processing. So why developers love so much Kafka and why they choose Kafka? There are 4 main reasons for that. The first one is scalability and the performance. So Flink runtime architecture is designed to handle actually limitless scalability. That's by doing parallelism into potentially thousands of tasks, as we can see here. Each of these tasks is distributed and executed concurrently across the cluster. Okay, there's actually a Flink cluster. This parallelism is managed by the Flink runtime, which allows scaling up and adding more machines to the cluster to increase the processing power. And we can see that we have few components that actually take care of this. We have the job manager that coordinates the executions of the task across the cluster. We have the task managers, which actually is the worker nodes in the Flink cluster, and it's responsible for executing the tasks and doing the actual work. And each task manager has multiple task slots, each capable of running a partial instance of the task. And finally, these results are aggregated and go back to the client. These are the results that are coming back to the client after the job is done. Flink also leverages in-memory for performance. So Flink stateful applications, when you're doing actually aggregations and things like that, need to have some way of managing state, okay? So Flink stateful applications are optimized for fast access to local state by maintaining task state in memory or in disk, which results in low latency processing. By actually leveraging in-memory performance, Flink can process the data quickly and efficiently, making it ideal choice for real-time applications that require fast response time. So also Flink's in-memory support is well suited for use cases that need iterative algorithms or machine learning, where data needs to be processed multiple times in a quick succession, meaning that we need to access this data again and again and again. So when it's in memory, it's easier to access and reuse that data. The second thing is fault tolerant. Okay, it means that it actually can effectively that doesn't lose data and high availability. So Flink has two mechanisms for achieving that. One is called checkpoints, and the second one is save points, which are quite the same but managed a little bit differently. So checkpoints are actually maintained automatically by Flink, and they are executed periodically and doing snapshots to recover for quick recovery. And again, they're automatically managed by Flink. And save points are quite the same, but they are more handled by the user in case they want to do some kind of maintenance, whether it's upgrade or anything else that they need to do. And that's when save points are actually triggered by the users. So if, again, we look at the architecture, the job manager oversees the execution of a job. And if a task manager fails, as we can see here, the job manager will be aware of that, and it will assign a new task manager that will execute the job from where it left off using the checkpoints. And this ensures fault tolerance and ensures that the job can continue exactly where it left off without losing data or progress. Okay, so this is fault tolerant. This is probably the most interesting thing is the language support. Okay, so I talked about SQL, but Flink also supports Java and Python. But if we look at here at the diagram, we can see that Flink SQL is one of the APIs. But if we look from bottom up of this diagram, we can find process function. Process function is actually a primitive building block, which is actually directly manipulating Flink's state and timer. On top of that, we have the data stream API, which is sort of an abstraction, which abstracts these functions by streams and windows. And we have Flink SQL and table API, which are roughly the same or equivalent. But for the developer, the table API, you are actually writing Java or Python code rather than SQL. Actually, an interesting thing is that in Flink application, we can find a mix of those. Okay, you're not. You can use a mix of using table API and data stream API. You can do a mix of them, and that's usually what customers do. But a lot of use cases can actually suffice with SQL, Flink SQL, or table API, and just with that work. So, like I said, Flink, and actually Guy and Tal will speak about it as well. Flink SQL is an extremely powerful tool, and we think it's you can define both simple and complex queries with it, and it's actually well suited for most of your applications. And I'll shortly show you a demo of actually what you can do with it. So Flink SQL is ANSI SQL. It's making it easy for who knows SQL to work with it and easily connect to Flink SQL. And you can use Flink SQL to transform SQL statement like we see here at the right and create a Flink application. In this case, we're actually, if we look at it, there is the insert into results, which means that the data that will come out of this query will go into a table that is called results. And then we're doing the select color and count, which means that we want to group by the color and count the number of colors. And the where clause is how we do the filtering. Okay, this is how we do filtering in Flink SQL. And finally, there's the from, where actually with the data is coming from. And finally, the what Flink also offers is unified processing model. It can handle batch and also streaming in a single platform, and this is also very powerful capability. So Flink SQL also supports both streaming and batch processing modes, allowing developers, like I said, to use the same SQL queries for both batch and streaming. Listed here are some important differences between streaming and batch modes. So when choosing between them, we need to think about and consider the nature of the data and the application that we are trying to perform. So streaming mode is more ideal for real-time, of course, application and real-time processing of continuous data. And while batch mode is best, of course, for more static data sets. For example, we use streaming mode for use cases such as real-time fraud detection, like we mentioned before, in financial transaction, and use batch mode for generating financial reports, which run on a daily, weekly, monthly basis. So each mode has its own set of features and limitation. So we need to choose right, like and according to our use case. So if you know SQL well, then again, you can find yourself very familiar with everything that you might see here. And so the features that are listed on the left is features that that support both streaming and batch. And what is interesting that, for example, for stream processing, you can only order by time and nothing else. Whether on the contrary, in doing batch mode, it's actually you can order by anything you want, and there are special optimized queries that you can do with streaming mode that you can see here on the right as well. So last thing before I'll show you a demo is maybe for some of you are asking what is the difference between Apache Flink and Spark streaming. So there's few differences that worth mentioning. And so first of all is Flink is not doing micro batching, like Spark streaming is more like doing micro batching, and Flink process data in real time. Like I said before, Flink is proven to run in any scale, and running like in companies like in Netflix and Uber and so on. The SQL of Flink is more rich, supports more advanced features like temporal table joins and window joins. And this is the primary focus of Flink. It's not a side project, it's meant for doing stream processing. what is interesting is also that Flink goes well with the shift left pattern. Um, Data can be broader shared for several use cases, where compared to Spark, where the data is remain more locked inside of Spark, and it's harder to access the data from Spark. And the state management of Flink is more robust than Spark streaming. So let's move to a quick demo. I hope you can hear me still. So what we're seeing here is Confluent Cloud. I'll show the demo of Flink running on Confluent Cloud. So when we go to Confluent Cloud, we can see our environment, and here is my environment for this demo. So we have connectors that are inserting data inside our platform, okay, our DSP platform. It can be anything that you want, you know, data coming from your database or applications and so on. And these and the data comes, of course, into Kafka topics, as you probably know already. Okay, so we can see the data coming inside here. Hopefully soon here you can see the data that is coming in. And now let's see how we interact with Flink. Okay, so let's go here and go to Flink. So first of all, every topic is actually presented as a Flink table that you can access and do manipulations on top of it. So if I run the command show tables, I can see all the tables that I have running in my cluster. Okay. And now I can do all kinds of manipulations that we talked about, whether if, let's say I want to check the first 10 orders of our customer or something like that. Okay, so again, we can see I can select the data that is of interest to me from the table, and I can do also a where clause to filter the data for a specific customer, for example. Okay, so if we run this query, we will have data that is only for this customer, and this is a way to interact with it. It will probably take a few seconds, and then we'll get the data coming in. And again, this is data. It's not like an SQL query that you run once and you get the answers, and then that's it. You see, data is always flying in and always generating. Okay, so we get, whether it's you want an active dashboard of the real-time data, you see how easy it's done, or whether you want to create a new topic from this data, you can do it as well, and I'll show you in just a few seconds. And this is another example of doing tumbling windows. Okay, so we talked about it. If we want to do something like the fraud detection and so on. So this again, if I want to see the amount of orders per 1 minute. Okay, so this is the way to do it. Again, very easy, not something very complicated, and also we get quickly the results and see the data coming in. Okay, now we will see it in intervals of 1 minute. Okay, and maybe let's see an insert into command. Okay, so this is another command insert into command is something that I showed also in the presentation, is to create a new, to take something coming from a stream, whether it's joining two streams or taking some data from a stream and making it and creating a new stream from it. It's the insert into command. Okay, so what I want to do is actually make the instead of the customer, which the customer can have multiple instances because we're having updates coming for a single customer each time he does a transaction or whatever. We want to make sure we only have a single customer. Then we can do here a manipulation and make sure that we only get it once. Okay, so this is actually inserting data coming from from one stream or a multiple stream to a new topic that we create. Okay, so then we can see that the data is coming to this new topic, which is called true customer speed, and then we can further create topics on top of it, and again create manipulations and manipulations over and over until we have our final product, data product. So this is how we work with the Flink SQL at least. In Table API, we can achieve the same things, but using Python and Java. But this works pretty much the same. I think that's enough from the demo.